Okay, good afternoon, friends. And today, what I plan to do is I'm actually starting a new way of recording the lectures. I want to try if this is good or bad. I don't know. Actually, we'll see how it comes. But the basic idea is I want to stress a little bit more on the Dirac equation. And that's the reason I'm trying to do it slowly. This is an important part. I want all of you to go through this derivation along with me. Um, okay, this part is, I'm repeating it. I'll be repeating it again today. I did it in lecture 6, which I'm sharing the slides with you. But I'll be repeating it again today, a part of it, uh, purely because I think this is an important point which we need some amount of stressing actually. Very good. So let's start with the Dirac equation. The Dirac equation comes from linear dispersion relation. Dispersion relation essentially is another word telling what is the relation between energy and momentum, nothing else. So what is the relation between energy, momentum, and masses, say, for example? So in the case of the Dirac equation, so what did he choose was this dispersion relation, was a linear dispersion relation because he wanted to avoid the problems in a quadratic dispersion relation and also the problems in assuming a square root. Okay, so he wants to avoid that problem of square root. And that's the reason why he chose this particular thing. Okay, so what he chose specifically was that E is equivalent to alpha. Alpha are some mathematical quantities which we consider to be matrices times P plus beta times M. This is the dispersion relation which he chose. Okay, so this particular dispersion relation where alpha and beta are some matrices. So he said that this should be true. Okay, so let's assume that this is the dispersion relation, and then let's see how far we can go. So to expand it further, so these are matrices alpha y, alpha x, alpha y, alpha z are three matrices corresponding to which multiply px, py, and pz. And beta is another matrix which multiplies mass of the particle. So here I want, again, I mentioned it in the last lecture, I'll repeat it again. The space, the spinorial space is different compared to the Lorenz space. So the spin half particles are not really the representations of Lorenz group S431. They are representations of some other group, which I'll come to today. I'll mention that in slightly more detail once I finish the recap, essentially. They are representation of another group, which is called a unitary group. So spinors are typically representations of unitary groups. Okay, the space where this Hilbert space or the spinor space is nothing to do with Hilbert space, with the Lorenz space. The Lorenz space has scalars, vectors, tensors, and so on. So, okay, but the spinors are given in a different space. Okay, I'm just stressing this again and again. Okay, so now the conditions on these matrices alpha and beta are such that alpha square should be equivalent to 1 and beta square should be equivalent to 1, so that you get back again your relation E square is equal to P square plus M square, which is the relativistic equation. So it means that all the cross terms which you can have when you square the right hand side, they should all go to 0. So all the cross terms which are alpha I beta plus beta times alpha, because these are matrices, they need not commute. So I have to consider these kind of relations. Okay. So these alpha I beta plus beta times alpha I should go to 0. Further, I also have within the alphas. Okay, within the alphas, alpha I, alpha j, and alpha j, alpha I. Also, there will be, because there are three px, py, pz. So you should have three alphas. Suppose if you go for 5 dimensions. So for example, if the space is 5-dimensional, you will have px, py, pz, pz prime. Or if the space is 2-dimensional, you'll have px, py only. So there will be only two alpha matrices. So in a 2+1 relativistic theory, it will be a different set of alpha matrices, and it will be a different set of gamma matrices which will come up. Similarly, if so, the number of dimensions of space and time also determine then the number of gamma matrices you can have, and the dimension of the spinors you can have. Okay. I stress this point again. Essentially, so the number of dimensions. So if you have 4 space-time dimensions, implies 4 gamma matrices or 3 alpha and 1 beta matrices. Okay. So the number of and that also determines what is your spinorial representation, meaning what is the dimension of the spinorial representation. So if these conditions are met, you have the first equation in the differential form. Okay, this is in the differential form where I is E, I represented by the time derivative and the Hamiltonian essentially, and the momentum I represented by a space derivative. Okay, and I put it back in the equation. These are operators, and time operator, which is the Hamiltonian operator, should be equivalent to the momentum operator times psi times beta times psi. So now I really wrote it in terms of operators acting on a Hilbert space determined by the psi. Psi is the wave function or the Hilbert spaces essentially. So once you write it in terms of these operators, you end up having this particular relation. There is some error here. There should be an m here, beta times m here. Okay, so you write beta times m. So you have, this is sort of correct. So beta times m times psi. So this is an operator. This is a differential form actually. Now, what Dirac looked at is we had to look at solutions of this alpha and beta. Okay, and as we have mentioned, that alpha and beta should be Hermitian because they are in the Hamiltonian. So since they are in the Hamiltonian, they should be Hermitian. So alpha and beta are, so you have these conditions that alpha I dagger is equal to alpha I, beta I dagger is equal to beta, and so their eigenvalues are real. And also these are matrices whose squares is equal to 1. There is a special name for it. I don't pretend actually. So it's alpha I square is equal to 1, beta square is equal to 1. So it depends upon the power essentially. So we can easily see, because you can always go into a basis just by arguing that the trace of any matrix should be equivalent to the sum of eigenvalues. Okay, so if you go into the diagonal basis of these matrices, okay, so our A dagger is equal to 1 because they are also Hermitian, plus a square is equal to 1. So this gives me the condition that the eigenvalue should always be equivalent to plus minus 1. Actually, they cannot be anything else. So if you take A dagger is equal to 1 and take, say, for example, the sum of the determinant of the eigenvalues on both sides, you will get a determinant of the product of the eigenvalue should be equivalent to 1. and the product square of the eigenvalue should be equivalent to 1. So this means the eigenvalues themselves should be equivalent to plus minus 1. So you just take determinant on both sides. Determinant is equal to product of so using that, and the determinant of matrices det A B is equal to det A det B. So this implies that A square or that alpha square is equivalent to that of unity. So from this you end up this relation that the eigenvalue should always be equivalent to plus minus 1. Now you can also show that the trace okay, also given that alpha I beta and beta alpha is equivalent to 0, you end up with a condition like trace alpha I trace sum of the eigenvalues should end up with something like beta square alpha I, because beta square is equal to 1, so that is equal to trace beta alpha beta, okay, and because it becomes minus 1, okay, beta beta minus 1, and then so this gives you a contradiction from this relation that the trace alpha I is equal to trace minus trace alpha. Okay, we can just verify this. 1 second, give me a second. So this is alpha I is equal to beta square alpha I. No, that's right. So this is 1 second. So the trace you can is the same when interchange. So trace AB is equal to trace BA. Okay, I think instead of going through this, we can just ask. Okay, this we can cross check it. We can do it right away. Okay. Okay, but you can do it. Okay, it's easy. We'll end up with a condition that trace alpha I is equal to minus trace alpha I. So this trace should vanish. Trace alpha I is equal to 0. Trace vanishes. Okay, I can. Okay, so for that you have to use the commutation of the trace and the anti-commutation of the matrices. So if you use these two, you end up with having this relation actually. So with this, you have this bunch of conditions that these alphas and beta should be Hermitian, eigenvalues plus minus 1, traceless, and the anti-commute. And you can start with a bunch of matrices. Let's just take the most general matrix A and say that, okay, first of all, when have this, you know that it's all should be 2-dimensional or 4-dimensional or 6-dimensional. They cannot be odd dimensional matrices. So you have A dagger A is equal to 1. So if you have assume that if it is a 2-dimensional matrices, so you can still see a simple formula like, say, if I take A is equal to A11, A12, A21, A22, and then you put all these conditions. A dagger is equal to A square is equal to 1. So this would mean, okay, and trace A should be equivalent to 0. So you can actually take a complex bunch of matrices, okay, all these conditions. You can actually work out what could be the thing. Say, for example, A dagger is equal to A implies A11, A12, A21, A22 is equal to A11 star, A12, um, this is sorry, A12 star, A21 star, A22 star. So this would imply A11 is equal to A11 star, A12 is equal to A21 star, A21 is equal to A12 star, and so on. So A22 is equal to A2 star. So that means A11 is real. So you end up having a real matrix, a real element for A1. A21 and A21, they should be Hermitian conjugate of each other. And so you end up with just a simple function that it is a real number, real. So A12 star. Okay. So this is this reduced suddenly. You instead of having say 2 2s, 4 2s, essentially you have 4 elements to 8 elements. You end up having 2 to 4 elements. So it reduced the entire number of parameters to 4. So you put in all these other conditions, you end up having only possibilities. You can then look at all the possibilities, and all the elements should be plus minus 1, right? Essentially, because you also have the eigenvalue should be plus minus 1. So when you do all that calculations and look at all the possibilities, and they should anti-commute with each other, you only end up having for n is equal to 2, 3 possible solutions. This is a very nice solution, and these solutions are nothing but your Pauli matrices. So sigma x, sigma y, and sigma z. Okay. Now the easiest other next possible n is equal to 3 is not allowed. Like I said, the odd numbers of matrices is not allowed. You can cross check it why it doesn't allow, because it won't satisfy these conditions. See, if you go into the third condition and the 2 condition, if we take these 2, it means that they should be even dimensional. Because the trace of a matrix is equal to sum of its eigenvalues. Okay, if it is traceless, means the sum of the eigenvalues should go to 0. Okay, you cannot have eigenvalues which are 2 and so you end up having even dimensional matrices. So if 2, there are 3 possibilities, but we need 4 such matrices, and they're only possible in 4 dimensions. So 4-dimensional matrices you can easily construct starting from the solution what we have from 2-dimensional matrices. So this is like a direct product of sigma I times alpha I is equal to sigma I times what is this matrix? Sigma 1. If you take this one, that gives me alpha I. So this you can write it in terms of this one. Whereas beta is what? A direct product of sigma 3 times 1. So this is another way of representing the alpha and beta matrices. Okay. So you're starting with the solutions of the two-dimensional solutions of what we know, but because we need 4 matrices, you can construct it in this particular fraction actually. So so you get these 4 matrices, which I represented in this particular fashion actually. One can represent it in this particular fashion. So alpha I, there are 3 alpha I, fourth one is a beta matrix, and the Dirac equation is this particular fashion. And if we expand this, this gives me sigma dot p 1 plus m psi 1 psi 2 psi 3 psi 4. And these wave functions psi 1 psi 2 psi 3 psi 4 all called spinors. So what are spinors? Spinors are okay. Spinors. So let me digress a little bit into what are spinors. So spinors are something called fundamental representations. This is the technical word. Unitary matrices. Okay. Groups. Say for example, if we have a SU2 group, which is the spin group, which is not a, okay. Anyway, let's just consider it as the spin group. Okay. The representations of this thing, the spin, the vector functions, vector space on which the sigma matrices are defined is the spinor. So what is a vector space you define? So you define the vector space is essentially, say for example, for sigma x, sigma y, and sigma z, the vector space is nothing but 1, 0, 0, 1. This is the vector space. So this is the vector space, and using this vector space, on this vector space you define the sigma matrices. So the wave functions of the spin wave functions are always given either in the terms of, maybe there's a normalization factor, up to a normalization factor. Okay. In terms of 1, 0 and 0, 1. Okay. And so you have sigma x, sigma y, sigma z, these 3 what are called the spin generators, or spin generators of spin. These are represented in terms of this particular wave function, or this control of column vectors, okay, wave functions, which are called spinors. These, since they have 2 components, they are called 2 spinors or 2 component spinors. Now, what has Lorenz group to do with it? The Lorenz group, what is the connection between the Lorenz group and spin group, or the rotations, derivations of the spin? The thing is, if we have a SO31, which we saw it as the Lorenz group, is connected. There is a mapping, okay, to SO31 to SU2 times SU2 by Z2. Okay. So the Dirac spinors because there is a one-to-one mapping, a one-to-one and onto mapping. onto mapping. So we are not looking at the Lorenz group directly, but you are looking at an equivalent group. If you want an equivalent group in complex space, spinor space, and this is what, these are the solutions of the Dirac equation which Dirac has discovered. So what you're looking at, you're still looking at wave functions which satisfy the Lorenz group, okay, the Lorenz symmetry, but they're actually of a different kind, because they are discovered as a in a separate space, which is the spinorial space, which is an equivalent group of Lorenz group, but acting on a different kind of a vector space. So it is a different group. Okay, it's acting on a different vector space. So this spinors come out as representations of Lorenz group when you consider them as some unitary groups, essentially a unitary mapping of the this SO31 group to SO2 times SO2. Now, as of now, I won't go into greater details. We will have uh, uh, elements of group theory coming along. Actually, we'll do elements of group theory as we will progress. During that time, I'll spend more time. Okay, so this is just a digression to introduce you what spinors are. Okay, so just to get a picture of what spinors are, and but anyway, we'll continue. We'll go into the greater details of these things when we'll do elements of group theory. But for the present, this is like just a definition of what are spinors. Okay, so the Dirac spinor is also a representation of the Lorenz group when Lorenz group is considered as some other group, okay, as some other equivalent group, which is called SU2 times SU2 by Z2. Okay, okay. Don't worry about the notation, but just see it as a direct product of two SU2s. Okay, forget about the Z2. We'll come to it a bit later, but you can think it as some two direct product of SU2s. Now, the important point is, because it's for a moment, we'll come to it later. So what we have seen is it's a direct product of two groups. So each SU2 of the Lorenz group of there are two SU2s, SU2 times SU2. So the Dirac equation or the Dirac spinor contains one SU2 on the top, another SU2 on the bottom. So it is made up of two SU2 spinors. So it is a four spinor made up of two component spinors. Okay, this is a slight detailed, but anyway, just to get a feeling for what you're going to see, this will make sense actually, because as we'll do the lectures now, as we'll go into looking at the solutions, we will see the grouping of in terms of two component spinors. Okay, then that why I made this comment will become clearer to you once you see this actually. So so what we are looking at is so these are the four spinors of the Dirac equation. The wave functions are four spinors. Again, the spinorial space is different from a Lorenz space. Okay, there are four Lorenz because there are the gamma matrices do carry a Lorenz index, but it's just but they are four dimensional, but they are more related to the number of space dimensions. but their space is completely different. For example, if you go to 5-dimensional spaces, you'll have 5 gamma matrices, but the space of each of the gamma matrices would be 8-dimensional. So the space, so that means the vector, the spinorial vector would be 8-dimensional spinor. Okay. So it all depends upon what these are. The only possibility, you don't have 6-dimensional spinors, but you have 8-dimensional spinors, and so on. So okay, you have 2-dimensional, 4-dimensional, 8-dimensional. Okay, so on. So you can, okay, in principle you can have 6-dimensional spinors also, but it's a for space-time dimensions I'm talking about in relation to it, space-time dimensions. Okay, so this gives you this thing. So then we introduce the gamma matrices, which are the main notation which we always use. So the gamma matrices are gamma 0 is equal to beta and gamma I is equal to beta alpha I. So gamma 0 is nothing but beta. So this now, if you write it in terms of the notation which I said, so this will mean gamma 0 would be 1 is 1 minus 1. Okay, this is nothing but 1 times sigma 3. Okay, this is minus I sigma 2, I sigma 2 times sigma I. Okay, gamma I is equal to I sigma 2 times sigma I. So this is the times, this is a direct product. So this is a direct product. So with this, the Dirac equation, where I use the slash notation, the slash notation is del slash is equal to del mu gamma mu, and gamma mu is equal to gamma 0 gamma I. Gamma I is anti-Hermitian. Anti-Hermitian is gamma I dagger is equal to minus gamma I. Gamma 0 dagger is equal to gamma 0. Why it is anti-Hermitian? Because gamma I is equal to beta alpha I. Okay, when you take the dagger, you pick up a minus sign actually. Okay, because alpha and beta I anti-commute, because the commute. So, with this definitions of all sigma matrices and gamma matrices, the last time I wrote down, this is the solutions. We were looking at static solutions essentially. So we got the first bunch of static solutions, which are essentially where there is no space variation, and what we did do, we got the easiest solutions would be just to assume that the derivatives with respect to space just vanish. And in such a case, so I divided this into terms of two component spinors, psi A, psi B, and then I re-express this equation in this particular fashion, and you see that equation nicely decouples if I just assume that del of the space dimensions vanishes, and so this will be just proportional to psi A will be proportional to itself, psi B will be proportional to itself. Now this will change a moment we'll see. So we'll have the simplest plane wave solutions. This will change moment we relax the assumption. Okay. And so this gives me uh, uh, these kind of solutions. So the plane wave solutions. Sorry, am I think there's some error in the recording. So again, I'm saying somewhere I went silent, I think. So this is again del by del t minus Im psi a. So what I'm saying was that psi a will be proportional to psi a. The derivative of the psi a will be proportional to psi a, and psi b will be proportional to psi b. Now you can integrate it, and you end up with solutions in this particular fashion. Notice that there is a minus sign difference between psi a and psi b. If psi a represents positive energy solutions, and psi b will represent negative energy solutions. So negative energy solutions will not go again. So the moment you consider um, relativity, so any particle which is relativistic, so you should have both positive and negative energy solutions. So psi a and psi b, they look like two component spinors. So these are exactly like spin states, which we have said, like the SU2 thing. So with that, we wrote down these four solutions last time. Essentially, these are your positive energy solutions. The yellow ones are your negative energy solutions. And then we stress the fact that negative energy solutions just don't disappear. Now, I wanted to report this part by setting a few more things, essentially. Um, so I have done that. Now we'll start, okay, with uh, uh, this one. So look at plane wave solutions of the Dirac equation. Now, the reason for repeating was that we are looking at static state solutions, and the solutions are in terms of the spinors. And the spinors, I said, essentially we'll be looking at. So what we are looking at, the solutions of the Dirac equation are plane wave solutions. So what you would have, you would expect the Dirac equation plane wave solutions to be I del slash times A e power minus I kx u of k. Now, how did I do that? This is some normalization factor. So, and then this is some 4 spinor. So I would say general plane wave solutions of the Dirac equation are of this particular format. Where e power I kx is equal to e power I k mu x mu. So this is e power I k0 x0 minus k bar x bar. So this is with this metric actually. So the matrix is 1 minus 1 minus 1 minus 1. Metric. I think I'm just doing the opposite metric now. Okay, the one compared to the one I had started off. Okay. Um, I think I did the Klein-Gordon equation in the other metric, but I'm doing this this metric in this fashion. Now, the Dirac equation in this fashion. So now let's When I wrote it like this, I mean the diagonal is 1 minus 1 minus 1 minus 1 0 0 for this all the other elements. Okay, so let's now continue. Now, how did I make this claim? I made this claim based on what we saw in lecture 6, essentially that uh, that uh, if you take the simplest solutions, say for example, when all the space derivatives are set to 0, you end up having with a solution which looks like uh, say for example 1 0 0 0 0 1 0 0. So this is a space part. So e power minus imt, e power minus imt. There are these 4 solutions, and so this is multiplying this particular only one part. The rest of them are 0. Okay, plus imt. Now you have to be careful by saying, when you say the rest of them of 0, can I neglect them? No, no, no. It is not equivalent. You cannot neglect them because it is in a different space. This is a space in which these are just entries. We are just saying that, okay, these are the 4 solutions we have looked at. Now, the point is that, so this part looks very similar to the solution of the Klein-Gordon equation. The reason is simple. The reason turns out that I won't derive this in detail, but I'll just mention it here of the Dirac equation is the Klein-Gordon equation. What do I mean that is that if I start with Dirac equation, ideal slash minus m psi is equal to 0. Now we take the conjugate operator and act on it. Del slash plus m. Okay, on it. This ends up, okay, because it's the square of it. So you should get back Klein-Gordon equation. So suppose if psi is equal to psi 1, psi 2, psi 3, psi 4, you'll have del mu minus m square psi I is equal to 0. So psi I here are psi 1, 2, 3, 4. So that means each component of the Dirac spinor so what it means is that each component of the Dirac spinor satisfies the Klein-Gordon equation. You can actually show this. Okay, you can actually explicitly show this by the trick I showed you. Okay. Okay, since I'm not proving it to you, I refer to you some books like, I think you can look at, refer to, say, relativistic quantum mechanics by Greiner. It has it, I think, also Zix and Zuber. Okay, but if you are interested, but it doesn't really matter for us. Okay, if you are referred to Zix and Zuber, relativistic quantum mechanics. Maybe I made some error somewhere, but by Greiner. Just check. Essentially, you just refer to this and where the derivation is given, but you can actually work it out. Actually, when you can write the entire full matrices, multiply them, and cross check. If I have made an error with the minus sign or something, just cross check it. Okay. So this is known in simple terms as the square of the Dirac equation uh, is the Klein-Gordon equation. Okay, that's what it's. People try to remember that. Okay, the square of the Dirac equation. So with this in, you can keep this in mind. But okay, so this is one sort of a justification to believe that the solutions or the plane wave solutions of the Dirac equation are like, say, we can say that there will be some psi of x is equal to some normalization factor e power minus kx. Kx means kx mu u of k. Okay. Now, will this work? So let's put it back into the Dirac equation. So when you put it back into this, into the Dirac equation, you have del mu psi is equal to minus say k mu psi, putting psi back into so you get I k slash minus m times u is equal to 0. So u is the force spinor introduced here. Okay, introduced here, u, okay, u of k. This is called momentum space Dirac equation. Now, the remaining part of the derivation I'll just follow from, I think, Griffiths or one of these. So it's a very standard derivation. You can also follow from Bjork-Nendrel or look at relativistic quantum mechanics by Dreiner. But I think we don't need that kind of expertise as of now, unless you are specializing in particle physics. Say for all of us, I think remaining party, what we can look at is just look at Griffiths. Okay, Griffiths book. It's very well done, actually. So we start looking at this. Let's expand this momentum space relations. So we have I gamma mu is equal to, we know the definitions of the gamma mu, right? We have done it in great detail. So it's nothing but gamma 0, gamma I, and then we have gamma 0 is nothing but beta, which is 1, 0, 0, minus 1, and the gamma I is 0, sigma minus sigma I 0. Okay, so let's go back to the momentum space Dirac equation. So I multiply with k. So gamma p slash or k slash. So okay, k I'm just using. I think this is what Griffiths uses, if I remember correctly. But in many other textbooks, it's just the momentum space is written in terms of p slash. It's just matter. It doesn't matter what is, whether it's p or k or not. These are the standard formula, which is there in every place, essentially, that we have k0 minus k0 coming from the beta part, and the k1 ki part would be given by minus k dot sigma bar plus k bar dot sigma bar. So okay, so this is clear now. There is a minus sign here in the gamma I, and also there is a minus sign coming in k0 gamma 0. Okay, so this is gamma 0 minus ki gamma I, and so this is what you get. Okay, now you have the full Dirac equation, ik slash minus m is equal to times u of k. Now let's write it in fully. So this gives me this matrix we have seen. The diagonal elements will have k0 minus m minus k0 plus m sorry, minus k0 minus m minus k bar dot sigma plus k bar dot sigma ua of k ub, let me call it as ua and ub. Okay, so this should go to 0. Okay, this is what the Dirac equation tells you. So let me express it right. This gives me two coupled equations, unlike in the case where the space derivative goes to 0, you don't have any coupling between u a and ub. Now you seem to be having coupling between two, meaning both of them actually. So this gives me, so k0 minus m times ua of k minus k bar dot sigma bar times ub of k. The second equation is k bar, okay, I bar dot sigma bar ua of k, okay, minus k0 plus m ub of k is equal to 0. Okay. So this tells you that, okay, I'll again make the point, stress the point that now you can see that UA and UB are not really sort of separate from each other. So now again, you have, okay, you can ask the question, what is the relation between UA and UB? So from this you can get UA is equal to, okay, UA of K is equal to 1 minus K0 minus M, okay, K bar dot sigma bar times UB. Similarly, you'll have UB of K is equal to 1 by K0 plus M K bar dot sigma bar UA. Now you all agree with this, so this part. So K bar sigma. So you end up with so I can put say for example the definition of UA into UB, okay, and UB is equal to UA. So you'll get a square of this. So you'll have a second equation, meaning higher order equation. So if you put this thing, UA of K is equal to 1 by K0 square minus M0 M square K bar dot sigma bar whole square UA. Now this is an interesting identity. This just gives you the information which I mentioned to you earlier. K dot sigma, we know what it is. K dot sigma bar would be what? Is equal to K square times 1. So K bar dot sigma is K0 bar. Okay, this we have seen, I don't know. So if you have any vector, say for example, this we can do it other. Okay. So if you have a vector R bar, this we'll do it in even classical mechanics. X is equal to during the rotation group also we'll do it. But anyway, just let me just repeat it. So R bar dot X bar dot R bar dot sigma is equal to RZ Rx minus I Ry Rx plus I Ry minus Rz. Now R bar dot sigma square would be this is a well-known result. This gives me R square times 1. Okay, this is sort of a well-known result. Okay, so using that I have, so you see this just gives me K square by U of A. K should give me k bar dot sigma bar square, that's just k square, is equal to k square by k0 square minus m square dimensional. It's fine. Yeah. Okay. So this again gives me the same relation. In another word, k square gives me the same relation. K square is equal to k0 square minus k bar square. Okay, this is k bar square. Okay, k bar. I had to be careful here. Mod k bar square. Okay. Is equal to m square. This is small k mu by the way. Okay, in case you're all confused with the several k's you're having. So this is k mu k square, that is equal to k0 square minus k bar square is equal to k square. Okay, this gives you small. But now I need to start with this and start representing these solutions. So I want to look into solutions. So for the momentum space solutions, I just pick the relations as follows. So choose UA because I can choose my spinors as 1, 0. Then putting it back in UB is equal to 1 by K0 plus M K bar dot sigma bar times UA. Okay, this is what I had, no? So this gives me, this is P dot sigma or K dot sigma. So we know the result times K0 by, so let me just choose. So 1 by K0 plus M times K dot sigma, I wrote it down. K bar dot sigma is minus Kx, Kz minus Kz, Kx plus Iky, minus Iky minus Kx plus Iky, Ky. Then UA I choose to be 1 and 0. So then I have Kz multiplying 1, that is 0, and K0 is equal to 0. And this will be a column vector. And K0 is equal to E. So this is your K0 is equal to E, the energy of the system, of the particle. So UB is equal to, we have the first solution, 1 by E plus M K, this is Kz, okay, Kz and Kx plus Iky. Okay, so now if I choose, so you have four solutions. One, UA is equal to 1, 0. Then I have UA is equal to 0, 1. Do the same thing, and you have UB is equal to the solution C, meaning 1 by same thing, E plus M, but now it will be the reverse on the top. P Kx minus IKy, Ky, and then you'll have minus Kz. Okay, and then choose UB is equal to 1, 0. So let me write down the four solutions systematically. So UA, so UA is equal to 1, 0. I'll have the solution to be UB is equal to 1 by E plus M P Kz Kx plus IKy. So the full solution would be, so the full solution would be, okay, let me write two of them together, and then another two, UA is equal to 0, 1. Okay, UB is equal to 1 by E plus M Kx minus IKy, okay, minus Kz. So these are your positive energy solutions, and then you have another two solutions which are UB is equal to 0, 1, and then UB is equal to, oh sorry, I think we should take 1, 0 first, right? We are taking 1, 0, and then 0, 1. In this case, UA would be, using the same solutions, 1 by E plus M hello. Yeah, I'll be there at 3 o'clock. Hello. Yeah, so E plus M, just put it into not disturb. Okay, 1 by E plus M into Kz Kx plus IKy. Now UB is equal to 0, 1. You'll have 1 by E plus M UB is equal to 1 by E plus M Kx minus IKy minus Kz. So these are their four solutions, momentum space solutions. So the final thing would be psi, okay, in momentum space, Q of k is equal to e power minus ikx u of k, where u has this four solutions, so the ones which we have seen, where you have ua ub written Okay, so the first solution would be the full component would be, let me write one of them and you can write all the other things. So UA is chosen to be 1, 0, in which case the UB will become uh, 1 by E plus M into, let's use the standard notation PZ or KZ. Okay, let's just, because we have derived everything, KZ Kx plus I Ky. Now you can take the E plus M outside, so then you can take 1 by E plus M into E plus M 0 Kz Kx plus Iky, and so on. So you'll have 4 solutions. So this is one solution. Then you can do the for the 0 1 and then 1 0 and 0 0. Okay. Okay, so these are the 4 momentum space solutions which we have seen. So the 4 momentum space solutions. So now the first 2 solutions are positive energy solutions, and the next 2 solutions are negative energy solutions. Okay. Now Griffiths uses P mu is equal to plus minus K mu. Okay, but I will do it. So far, but we have seen the derivation of the momentum. Okay, but it's just a matter of notation. But again, to repeat, we have both positive energy solutions and negative energy solutions. I didn't come to the normalization. Now, what happens is if you do a U dagger U, I'll do this normalization again. Maybe I'll do it again. Okay, but I'll just introduce you. Okay, the normalization. Normalization. So if you take any of these solutions, it turns out the normalization would just become, you can figure out what the normalization factor is, root of E plus M. Okay. So this, I think, you guys can look into it. How do you get this normalization factor? Okay. This will be a homework problem, but anyway, so with this normalization factor, so you'll have the solutions would be, so normalization n times say 1 0. Okay, and then there will be pz by E plus M, and then px plus ipy by E plus M, and so on. And so this, okay, let me stop here. I'll repeat this calculation, meaning I won't repeat this calculation entirely, but Maybe I'll start with this momentum space again a little bit. You can derive the normalization factor. And then I will go further in this the covariance of the Dirac equation. I'll mention a few points and some representations and stuff like that. Okay. In Feynman diagrams and everything. What we need is this plane wave solution. These are the most important things which we need, and there are some properties of this Dirac spinors which we had to do. So once we know that, we have some handle about how to write Lagrangians with some interactions and stuff like that. Okay, so let me stop here today's lecture, and then we'll continue again later on. Okay, yeah, in the next lecture. Thank you.